So we're going to be learning how to find the electric field of a semicircular arc. So here's our arc.
But I didn't write this all over here, basically.
We're finding like the electric field from this point, like in the center.
Right, so I'll hold it up.
So this arc has a
So while you're
radius
looking
of
at the camera, you can read this.
has a radius of r. And first you can find the electric field at like one specific piece of the arc, like one tiny piece right there. And so the angle like for that small piece, you can call it d theta. Oops. D theta. And then for I don't know for okay. And then Shree's gonna talk about the linear charge.
Okay, so after we relate the differential piece, we can relate it to the overall charge and length of the arc by defining something what's known as the charge density, or lambda. And so charge density is defined as a differential piece of the charge divided by a differential piece of the length. And so we can relate this to the radius by noting that the differential length is just r d theta, and we know that by geometry.
I'll say we got Professor
Geometry.
Surreal.
And so we can also relate this entire equation to the overall charge of the semicircle by noting that the total length of this is just half of the perimeter, half of the circumference, or just pi r.
Future USC alumni.
Okay. And Rahul will now find the electric field.
Okay, so we can find the electric field because we know that the electric field is equal to the integral of k times the charge over the radius squared, dq, right? That's it. From over here, we can actually put this in terms of q and r, and by substituting that dq is equal to r d theta times lambda. So we have this is equal to k r d theta times lambda. And because it only applies in the vertical direction, because in the horizontal direction it's symmetric, it's actually going to be times sine theta. And now Ekin is going to perform the actual integration.
So for the most important part of this problem, we have to integrate this. So first, I'm going to move this out, this d theta out for clarity. So I'm going to do the integral of k r lambda over r squared, and then these r's can cancel out. So we are left with k lambda over r times sine of theta d theta. And we're integrating from the angles 0 to pi. So we're going to have 0 to pi, because those are our bounds for our angle of the semicircle. And since this right here is a constant and is not dependent on theta, we can take it out of the integral. So we can do k lambda over r over the integral of 0 to pi sine theta d theta. So the integral of sine of theta is equal to negative cosine theta. So we have negative cosine theta from 0 to pi. And then this, we can plug in our bounds. Equals cosine of pi minus cosine of 0, which equals negative 1 minus 1, which equals negative 2. So we're left with 2k lambda over r. And since this is pointing, since the electric field is pointing inwards, we're going to make this negative. So it's y, in the y direction. So this is going to be our electric field.